No.
Okay, I will introduce you. Welcome back, everyone. Today we have Ekaterina, and she's going to tell us about super Plucker embedding and cluster algebras. Take it away.
Okay, so thank you very much for having me here at this very nice semester in classical algebras. So I am, well, very much in some ways an outsider in this place. So it's my well, first and very first work in classical algebras. So I come from, from the side of supergeometry on this. And this is, I'm going to tell you something, so what I have for you. So it's a joint work with Ted Voronov. And what it is, well, we are trying to construct construct supercluster algebras. And I understand already have, we know there are several approaches to this. So we are trying to approach this problem from the point of view of Plucker embedding. So from Plucker relations. So what we try to do, we try to construct. So what we did, we constructed super Plucker relations in all cases. This is what we did super geometrically. And then what we're trying to do for a while now is to try to understand what we got and to construct some supercluster algebras. And we already have some prototype examples. So you know that we have relations. It's not very clear how to make cluster algebras of them. And so we have some examples, but that's also a question. I will show you. Okay. So enough of this. Okay. So let's see the following. So this is the structure of the talk. So first I will state the main results. So it's nice to say what actually was done and what was other people done. So then classical Plucker embedding, just introduce notations. So then what is supergeometry? And well, for Plucker embedding, we will need super exterior powers. And so I will explain you why you cannot, also in simple examples, simple terms, why cannot you introduce exterior powers in natural algebraic ways? And instead you have to construct something more complicated. And so then actually the results, so we'll do, okay, so we'll do, I'll show you how to construct super embedding. And so we did for all cases. And yes, I think we have a kind of, we have a suggestion, I don't know what it is, for supercluster algebras for the case of 2-0 planes in M space. But relations we have for that for all, but we just don't know how to. I'll just start. Okay, so what is the main result? So the main results, okay, again, so we constructed super analogs of Plucker embedding for the Grassmann manifold, supermanifold. So RS planes in M and embedded space. And one of the problems here was to figure out the target space, and the target space, instead of usual projective space, that turns out to be necessary weighted projective space. And this is, in fact, well, in the book of Manifold, in fact, years ago, it was written that it's impossible to construct Plucker embedding, super Plucker embedding. And so this result doesn't contradict us. But he's of course right, but we're also right because what we did, we just changed a little bit settings, right? So we changed the target space, so it started to be possible. Okay, so I'll show you that so we constructed super analogs of Plucker coordinates, which turns out to be also non-trivial thing. And then, okay, so here I would like to stress, just tell you straight away about the structure. So there's two different cases, which is not on equal footing. One is the case of, which I call algebraic or naive algebraic. That's a case of completely even planes in the super ambient space. And in this case, you will see, I'll show you the simple examples, you will be able to follow just naive algebraic approach, which is, I mean, it will still later on have some parties if you follow it, but you will be still more or less following the naive algebraic approach. But for the case where you have your plane, you have also potentially odd vectors which generated. when S is not equal to 0, you will have to develop much harder theory. And okay, so that's something, the last one, which also something we understand superclasses. Okay, so let's just say, okay, so reasons again. So here, so basically the slides why we are doing this. So okay, so you know that there is pretty much I saw our competition taught me here. So hello, Greg. So I know that Greg Musiker was presenting his versions of the cluster structure. So they come from the super decorated Tachmüller from Pence and Tinklin works. So they have their own suggestions. So I comparing, so they have others is different. So it's similar but different. So also Vali Ovsienko and then Ovsienko and Shapiro, so Li-Mixco-Shapiro, so they also had their own versions and then also something. So let's just.
I didn't present anything.
You didn't, but he didn't present anything. He's keeping it for himself. But the papers are available, so some people like me read them. So and then also there is like this team, so they also have their own version, so they presented some other comp. So you can, it's all available. Okay, so we get and so in principle, as in supergeometry by itself, it's also very interesting problem for us to construct a super version of the fundamental notion, which was by itself a very, very interesting thing. Anyway, so this is why this all happened. So Grassmann, so what is Plucker embedding? So you of course know everything about Grassmannians because it just was your bread and butter, but this is just fixed notations for you. So we have so real Grassmann manifolds, right? The space of r-dimensional subspaces, right? Say in Rn. And what is the Plucker embedding? You take so any element of this Grassmannian, so any r-dimensional subspace, say generated by say basis y u1, basis vectors u1 and ur, by vectors u1 and ur, and you map them into the wedge product of these vectors. Of course, choice of basis is not unique, but if you choose, as you know from linear algebra, you choose a different basis, then the determinant of change of basis matrix will speed up, will be a factor. Okay, so then if you consider projectivization, right, then this problem was also you have your well-defined map. And okay, so well, okay, so then what happens in the so if you this is a fixed notation, so I will also consider map U. So sorry, map matrix U. Matrix U is just when you take components of vectors U1 and UR and put them as rows. So it's a matrix U. And then if you do this way, then what does it mean that U maps, so this map, Pluck, maps U, right? So this to the minus. Well, because minus, again, you know, from linear algebra, if you do, well, in the exterior, R's exterior product of the vector space V, the basis is going to be what? E1, wedge E2, dot, 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 ER, and so on. So all kinds of wedges like this. And so you can do the algebra and the coefficients going to be exactly can be computed as determinants of the minus of this matrix. So that's a classical construction which you've seen in this community probably many, many times. I certainly see talks. Okay, so here's a specific example. Again, so let's consider the classical two-dimensional. So you see, I don't have a pointer here, but you see GR 2 and 4, right? So I use GR and GR. I don't know why both of them are just equivalent. So it just it's Grassmannian of two planes in a 4-dimensional space, right? So you see, so suppose we fix a basis, right, in an embedding space E1 and E4. So suppose L is spanned by two vectors, right? So L is mapped into the equivalence class of wedge product of V1 and V2, right? And so let's see. So okay, let's U1 and U2 expanded in this way in terms of so theoretically, of course, U1 and U2 doesn't need to be expanded. So this is components V1 and V2 relative to this base, right? But of course, well, you can choose, right? I mean, you have to talk about this, but anyway, so you can choose suitable bases such that you normalize some coordinates without loss of generality. Yes, it's true. Yeah. 1, 0, and 0, 1. So others similar. So you can normalize this way. Okay. So then, okay. So what is T12, T13, and T14? And so those are homogeneous coordinates, right? Those are exactly coefficients in front of the basis, right? So we consider here. So we map it inside second x3 power 3, right? So the base is going to be the E1, E2, E1, sorry, yeah, so we have 4 dimension, right? So E1, E3, E1, E4, and etc., 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 right? And so T1, T12, this is going to be exactly coefficients, at this, so this is just tells you which standard notations. Okay. So then you just do some algebra. So if you do the edge product, so you can express the homogeneous coordinates in terms of components of your vector U. So you'll get this, right? And then the last one, so each of them just basically relates for your coefficients of the original U's, and then the last one gives you some U information. So if you, instead of A3, you plug negative A23 and so on. So you get actually relation, right? You get relation between your coordinates. How you understand this relation, right? It describes your image in, so it describes, yeah, so it's a equation which describes the image of your map in the large, in the ambient space, right? So it's a projectivization of this one. So it realizes as a projective right. So, and this is normalized version. The reason I have such strange new correlations, just because I have here normalized it, right? So normalization can be understood by multiplying by this, matrix, by GLM2 matrix on the left. So if you, which multiply effectively minus by the same matrix. So if you divide that, well, so do some algebra, you get the standard correlation. Okay. Enough of this. So this was just fixing notations for me for this whole thing. Now for superspace. So for the, okay, so what is the supervector space? So supervector space, you can say just a space, vector space, where you have 2 subspaces. So V0 and V1, and V0 elements of V0 are called even, and elements of V1 are called odd. We don't consider usually in supergeometry mixed parity, like just because if you consider any problem in supergeometry in general, you could split it as a direct sum of 2 problems for just even for odd, and then you just, all other problems just going to be a sum of, split into this one. So you don't consider non-homogeneous objects. And okay, so if so, right, if we have this, so this one, the first line tells you just how to consider, okay, superspace over numbers. Now, if you want to have non-trivial coefficients, which we do, so odd and even, you just also consider some auxiliary commutative superalgebra where the coefficients from your vector. So where the interesting coefficient is going to come from. Now, what is Grassmannian RS over V, right? That's okay. So then we put, remember this matrix here, where we put, so generators of my my RS plane. So my RS plane, right, has R even vectors generators and S odd, right? So I put them as the rows, and the columns, right? The columns has to correspond to the basis in the ambient space, right? So I have M even columns and M odd columns. Okay. Now, from just from consideration of the parities, you could see it's very easy. So these elements, which is in this block and in this block, has to be even. So this is all even elements of the superalgebra A, and this is odd. Okay. Very similar to what I showed you before. If you want to find dimension of such supermanifold, so you consider in one chart, you consider, so this is in one chart, you have So you normalize it, this matrix, by multiplying by, well, elements of GL RS times RS, well, very similar idea. So you create, you know, identities and zeros here, identity matrices and zero here. And so the rest of the elements going to be these coordinates in this chart, and similarly in all other charts. So you have the coordinates, and you can compute the dimension of this supermap. Okay. Now, as you understand, if we want to, if we want to construct super Plucker embedding, which we needed, as you know, we need for super Plucker relations, we needed to figure out what is going to be. So in this, for some reason, this thing don't show you the titles, right? And they.
So you put up the, like, if you put it on the way down.
Okay.
Somebody needs to sit down.
Okay. Let me. I'm not sure what I did. It was very strange.
I think it might also be true that you write on the board with online people can't see anything.
Okay. Well, all right. So anyway, so all right. So what happens is, so I want to consider. So as you know, well, I need super analog of. Sorry.
This one?
Oh, good. Okay. But because my titles is actually, informative, and so it was just and I don't repeat this information down. So, yeah. So okay. So problems with the definition. So you need analog of this for super situation, right? So what's the problems? Well, okay. So there's lots of problems, but let me illustrate it just with a simple example, simple possible example. Suppose you want to consider, okay, so 1-2 planes, right, in N-M space. Okay, so what's 1-2 plane? It's a plane which is generated by one even and two odd vectors. So here you see also my notations. So whenever you have indices with a hex, that stands for odd, and without hex is even. And then let's try to have a similar map, right? So we just map the L into wedge product of these vectors. If you ask me how I define wedge product, I just take a similar. I take a tensor algebra and the quotient by relations and just relations, anti-commutative relations, which is going to be slightly different. Of course, if you have a super, so a little bit, sign is going to be slightly different, but same algebraic construction. Why wouldn't it work? Well, because, well, you agree that if I define my map this way, right, then theoretically the same plane also can be represented by this vectors, right? Obviously. But if I make complications, right, compute wedge of this one, wedge product of this one, I have this, which is good, it's just this triplet of what we had here. But in super case, I have this term. Reason is because you have here, so in a classical situation, if this vector is will be odd, even, if this vector were even, in a classical situation, this term going to be 0 because you have anti-symmetry, so square is going to be zeros. But in the super situation, because you have for odd vectors, you actually have anti-commutativity becomes commutativity in the normal sense. So squares are okay and higher terms are okay. And this is pretty much in that community what people call absence of the top power problem, which actually manifests itself in different places, but it's what happens. Because when you have odd and even, then you have all this stuff. So you have this additional term, and you will not be able to define the map in this way. Now, this so you have to come with something. But before I go to the next slide, I'll tell you that in fact, this definition may work in some cases. In some cases, which cases it will work? Well, if I don't have this, and when I don't have this, if I don't allow odd generators for my plane L, right? If L not allowed, if only evenly generated, right? Then you never have the situation then your map is going to be well defined, and then you have that. So this one is exactly an algebraic case about which I told you before. So algebraic case is when you have completely even planes. So completely even means generators are only even vectors. But some people say, where is the super then? Well, the ambient space is still super, but you have completely evenly generated planes in the superspace. So that's where the split happens in cases. Okay. And yeah, so I'm going to use.
So for now, you assume that there are no attributes?
No. I consider all cases. This is easy, naive algebraic case. Yeah, but I think Windows.
You just click once on the slide and then
You better help.
so you can zoom back.
Okay, it's back.
Yeah. Okay, you can try.
Oh, perfect. All right. So let's leave naive algebraic case alone for a second, but we can cover it. And then let's finish up with construction of the exterior powers of the vector fields. What if I have S not equals to 0? So that's what problem was solved some time ago. And that's Voronov's large construction. So in fact, they constructed it for super differential force, but we just basically write all this, so but it's the same thing. So what's happening? So here they allude to the fact that okay, as you know, that exterior powers, they can interpret it as multilinear functions on covectors, right? So if you have a wedge product, right, this could be interpreted in one-to-one correspondence this with multilinear functions on covectors. So that goes to them from that direction, generalize them to supercase from that direction. So we say that F, right, is an element of the lambda RS of V, if and only if, right? So it's going to be a function. Multilinear, it's going to be a function, first of all, of even and odd covectors. So in even covectors, it's multilinear, but in odd covectors, well, there is nothing, or there is no such thing, but there is homogeneity of degree -1. And what does else know? If you inside your covectors, you're going to do linear linear change of variables, linear change of components. Basically, you multiply by GL or general linear group areas, right? So any covector substitute by linear combination of all of them. So you just spit out Berezinian of this matrix H. So Berezinian is a super analog of degenerate. Okay. And the second one is just the system of differential equations. Okay, so that's what we're going to use. Okay, so the thing about this F's, this functions F, is the following: that they define very abstractly, right? They are defined axiomatically, and so well, we don't have formulas. And of course, for practical things, we need formulas. But it turns out that we have some examples. So in fact, this space is infinite dimensional space, and so far it's open problem to have a description of such functions F. So nobody knows how to descriptions. And however, we have some particular examples of such functions. And specifically, well, there is example of one of such functions. So how this functions is defined, one of such functions. Well, if you take, so this, by the way, function, which I'm about to present you, is going to be in some ways analog of, super analog of simple multivector. So it's analog of wedge product. So it's how we're going to do wedge operation between given vectors. Not just instead of wedge operation, we consider the corresponding function F. And this function is going to be defined by its action on covectors in the following way. We just consider pairing, right? So we consider Berezinian of the following matrix, where AIG element of the matrix is going to be pairing between UIs and. Anyway, so here you need to know, I already told about Berezinian. Berezinian is well, it's not the same formula as determinant. So it's so it's highly non-trivial analog of determinant. And one thing you may need to know is that it's actually unlike determinant, which is just a polynomial in entries of the matrix. Berezinian is the rational function. For example, that's what you may need to know. Okay, so that's okay. And yes, so that's a proper generalization of the wedge product. So if you substitute s equals to 0, you get up to normalization factor. You just get a wedge product of the function corresponds to usual wedge product in the classical case. So it's a nice generalization. Okay, back to algebraic case, which is, well, yes, we consider. And so in algebraic case, we obtain, so it's completely even planes. So you see planes are generated completely by even vectors, so we have a complete set of super Plucker relations. You don't need to copy it, it's in our hive. So you can just see it then. So then if you have, for example, if you want to have a more human looking things, so if r equals to 2, for example, 2 planes, which most of you are interested, so here is the relations of the vector. Yeah. And again, it's all in our hive. I posted slides. So, all right, so specifically, even sub-example of this example, right? Because this example is still for large embedded space, so MF. So if you wanted even more, you can, let's consider 2 planes in 4-1 space. So then you have this relation is going to be this one, so you can rewrite this one. And you see that you have some awkward relations. So, you know, for example, 1, so remember that with heads, you have odd. So 2 heads give you even. So you have even nilpotent in the first one, then this one, so we get some kind of much. So this one mentioned that this particular example for 2 planes in 4-1 space, considered interestingly by Cervantes, Rita Ferreira, Toledo, so they are physicists and they considered this in kind of physics paper, and they considered this particular example. But they came this particular, but they came to the same set of relations, but they boast some pretty different directions. So okay. So how much time I have, because I want to go to. Okay, good. So this particular computation I can show you later if we have time, but let's just go first. Okay, so now as I said, okay, are you going to consider only the simple case? No. We're going to consider a general case. And the general case is going to be the following. So first, let's, okay, so you're seeing that we have, okay, so then we have this examples of functions f, right? So what we're going to do, we're going to map, okay, so our, so Pluck, what is going to do, is going to take vectors u1, ur, u1, 1 hat, us 1 hat, and map it into this function, basically into simple multivariate. So it's not very nice here, but it's just you take L, you take its generators, one of this bases, u1, ur, and then you map it into simple wedge product as I described above, which is simply mapped into bare u times p. You can think about this way. So you make matrix U as we've seen before, as the rows made of u's. P is made, if you vectors make the columns, you can see well, just the form. Okay. Anyway, so just to have here, it's okay. So here it's yeah. So here it's worthwhile to consider a specific example to just understand that it's not enough. And why it's not enough? Well, let's consider, so this I will show you detailed computation example where you understand how this construction works. And you also will see what's the problem, and then you just believe me that I think your own solution in general case. Okay, so imagine m dimension 2, dimension of your planes are 1, 1. Okay, so planes 1, 1, so generated by 1 even and by 1, 1 odd vectors. Okay, so we already have proposed embedding, right? So we have proposed Plucker map. So we want just to map every L into U1 wedge U1 hat, right? And so the question how we can check this, it's embedding. We want that it will be 1-to-1 correspondence with the image. So if you have this function f there corresponding to the plane, you will be uniquely be able to reconstruct the original plane. So this is what you want. So you want to be able to reconstruct, right? So we have proposed map. You should be able to reconstruct from the edge. Okay, let's set against the stage. So we have homogeneous basis examined in space V. Okay, so then you expand U1 and U hat. So here I used usually, I believe, physicists are using it. Greek are odd and Latin are even for the notations. And handled indices as just by notations are used for. Okay, so again, here to normalize, we have 1, 0 here, 0, 1 here, all similar way in one of the chart. And now here you see practical computations, how you're going to compute this function. Where do you send where I'm planning to send my plane? I'm planning to send my plane generated by U1 hat into function, which works like this. And here's the explicit computation of Grassmann. Okay. So what I want now, my local little problem is that will I be able, knowing how this function f works, will I be able to reconstruct my original plane? In other words, will I be able to reconstruct x, psi, eta, y, which will be the components of the use of the basis vectors used which generate model. Okay, so after some algebra, basic algebra, you will see that in fact, yes, you can reconstruct x if you just abbreviate your function on this character, you can reconstruct y if you abbreviate in this one, and it looks also nice and good until you have psi. And until you have psi, after some algebra, you see, okay, the only way I can restore psi, the figure out psi, I have to substitute inside my f odd vector, odd connector into the even place. So my function is only defined for even first argument, even connector, and odd connector at the same time. Now to reconstruct, I need to plug in here, I need to plug odd one. So in order to fix it, but here at this place, we could more or less easily fix it. If I recall that in fact, my function f, right, it was linear. Remember, it was multilinear in the first arguments, and it was if it was multilinear in first arguments, I can extend by linearity. So I have I can extend by linearity, and well, now I can correct my definition. So it was definition as before, but extension by linearity, and so I will be allowed to plug in odd connectors into as the first arguments. If so, then yes, psi I can also use. Now with eta, it's even worse. It turns out that you cannot do it. So to reconstruct eta, you need to plug in even covector into odd covector place. But the trouble is you cannot anymore expand by linearity because you don't have linearity. It's natural thing. You don't have linearity in odd covectors. So what you do instead, you can use this famous construction of Bernbel-Raven. So they propose to consider Grassmannian inverse together with Grassmann, which is, well, it's just when you have both blocks in your matrix, both blocks invertible, then they are just inverses of each other. But if you have in this blocked supermatrix, you have only one of them invertible, these guys, one of them exists and one not, and they kind of works in parallel. And they have symmetric properties. So if, yeah, it's very fast for you to understand, but pretty much this. So if the Grassmannian will be multilinear in the first arguments, then their star going to be the second type. So that thing swaps, and that allows to fix this. And I make a long story short because I want to go.
This is capable, right?
What is?
It's a power.
Oh, parity reversed. So it means that even rows start to be even odd rows, and because matrix have labeling, so even rows become odd rows, and same with column. Odd columns become even, so this parity is found.
But you make like even variables into odd variables somehow, and odd variables into even, or you just change?
Just exchange as well. So then okay, so how many minutes? Because I want to go as fast as possible. Yeah. So the yeah, don't worry, I will just start. So I have time to tell you about your favorite class objects. So then what we're going to do, right? So just this is the final definition, by the way. So our map Plucker is going to be what? Is going to be, well, basically yes. So we need besides just go back, since it allows me this previous not to work. Okay, so in not only I'm going to consider this one, but I also consider there with the stars, similar with the stars. Okay, so and this is just there, it's just written in abstract terms. So this is what's going to be my Plucker method. Okay, so I don't want to tire you with all that stuff, because that's here, okay, what do I have? So I showed you already Plucker relations and something which you actually interested in, right? Super Plucker relations in the naive algebraic case. Now we also have, so we put this is embedding, so it's uniquely like in this example, reconstruct, so it's going to be all good. And then we also take super Plucker relations. But formulas are large to present it here. However, I'm going to show you particular examples, a series of big examples, so you can see all of them. Again, everything in the paper are high field. Okay, so now towards your interest. So towards super cluster structures. So here is okay. So this is examples. You know what it means, right? So that's that. Do I need to tell? No, everyone knows too well, right? So see the picture, you understand what I'm talking about, right? Okay, so I'm going to construct. So this is in GR 2.6. So this something like so. Okay, so what we're going to do in supercluster structure, right? For 2, 0 in 4, 1. Okay, so what we have relations of this type, so number 8, which is just very similar, not very similar, exactly the classical Plucker relations, right? Which is which is different from Greg's and his team, and because he has something multiplied by this. Now for odd. Yeah, so let me just first say annotation, so I get myself excited. So let's first take the notations before further. So first of all, for even variables, there is anti-symmetry in notations. So if you have, when you start to write it down relation in A, B, C, if you see T4, 2, it's the same as negative T2, 4. Now when you start to write, like you have a classical relation, if you sometimes you have, I don't know, your T, so the one which you write, you're like, all right, this is like BD, and then it is something. And if at any in my notation that's T, and then if at any point you have here say 2 and 1, I would just flip them into 1, 2, and would write negatives. Just that. Okay, so what is theta? Theta again, that's the notations which we use for here. For specifically for superclusters. So and reason is because the ambient space, right? The ambient space have only one odd vector. So then you never have T1, 2 hat, for example, right? Because this is just a minor, right? So your matrix is going to have only one odd column. So anything odd going to look like this. So you have something and then 1. And therefore, your odd cluster variables always going to have this one. And just to stress that they are odd, we're going to introduce these notations. So this. So yeah, just to stress, because remember Greeks are odd. And though you have this, right?
Sounds like common sense.
So I'm going to say disclaimer. This conference doesn't support that. Yeah, Greeks are wonderful, and they're the best because the odd variables is the best. So
there's a question. Greg says,
hi Greg.
Is T1 hat, comma 1 hat possible here?
T
1 hat, 1 hat.
T, no,
1 hat, 1 hat.
no, because no, repeating no, not possible.
Not possible.
So that's, we use them one, but this one going to be so this one was thrown away because it's going to be even nilpotent, and so this one was thrown away. So what Kirk says.
Okay.
Okay. All right. So okay, so let me just show you the picture. Okay, so what do we have here? Well, all right, so so for this, okay, so this one are relations, right? So we have 2, 0 planes in 4, 1 space. So relations which we have for them is this ones. Everything else was for them. So we have 8, 9, 10, 11. So we don't know whether our suggestion is going to be. However, this is what we propose. We propose to have, in this particular case, just 2 clusters, right? And the clusters, so mnemonic rule for you, so we invented some mnemonic rule, how to think about this, is the following. Okay, let me just get through. Okay, so we have very similar to your usual pictures, but odd variables are dots on the diagonal. So they have to be, real diagonal. So you have a polygon and then you have diagonals. So odd dots, there's always 2 in this situation, and you, because it's 2, 0 in NM, and they can only be the ends of the real diagonal. Real diagonal, I forgot the word in English, but when you have this polygon, so this one is not real diagonal. But proper, okay, proper diagonal. But okay, so if you have any triangulation, like for some reason I wrote the simplest one, but anyway, so any triangulation, so as you know, in your usual case, this one clusters and this are frozen variables, cluster variables, this one frozen variables. But in my case, I have additional 2 odd cluster variables, and they allowed to be, this is how we parameterize it using the triangulations. They allowed to be only endpoints. The both has to be endpoints of the same proper diagonal. Okay. Now mutation rules. So perhaps this example is not very representative. I'll show you. It's it's a simple example. So it's outlier, right? So let me show you more more complicated. So more complicated pentagon. So there are 2 types of mutations. Okay, 2 types of mutations. Let me explain what's happening with odd mutation. So with odd mutation, we decided to pick just one of these, and this relation will be governing odd mutation. So what's happening? You see what you have one triangulation, another one, right? So here I don't need to explain what clusters are. So here's cluster T13, T14. It's even, and CT1 and CT4 is odd. Well, you all it could be. And so here, you see, so what happened here, 3 and 4 exchanges. Going from here, we do mutation in CT4, and it's jumped in CT3, and going backwards, so we checked that it's, involutive, so you go backwards, and if you mutate CT3, you're going to get back CT4. And the same is governed by this equality. So let's see. So T14 in denominator, I could check that was the diagonal, which is So when I show this, it's a very nice mnemonic. It seems to be between them. But again, we don't know how. So it's you say 1,4 is in here, right? So and we express CT3, so a new odd variable in terms of C4 and C1, CT4 and CT1, which is odd cluster variables. So it seems this way, and so 1, 3, it's another cluster, odd cluster, even cluster variable, and 3, 4 is false. So it looks like tip-top here, right? So it looks like nice, let's look, but there are two types mutation. So this one mutation, odd switched.
So theta 3 is again Grassmann value. It's plus 0.
Yeah, it's cluster. Yes, yes.
But it's not obvious for this. When you store it, can you see? Is it? Because you have
From this definition, you want to.
theta 4 squared is theta 1 squared. But you have mixed term.
So what happens if you if you multiply, I think it will squares to 0, because if you so squares, if you multiply one by another, squares will be gone, of course. And then when you multiply, you will have one term θ4, θ1, and another term times coefficient, and another term going to be θ1, θ4. θ1, θ4, when you swap them, you have a negative sign, so then you will cancel and get it.
You can mute.
Grassmann anti-commute. So Grassmann always like θ1.
What about Grassmann and even and odd? Do they commute or end?
Commute. It's just odd without give you minus,
It's
even.
different from the super technique.
Oh, it's different. Greg, is it different?
In super technique, odd and even anti-commute.
No,
Odd
I,
and-
I
So
thought in our case, even and odd also commuted.
Commute? Really?
Yeah, it was only odd and odd. Does that sound right to you, Nick?
Minnesota is. Yes, I think in that case it should be the same, because after all they do the same. I mean, they say they do the same super mathematics. It's just for different things, but they are basic stuff. Same, right? So that's excellent. Well, no, this one I'm sure they have. So
Nick also agrees. He said even commutes with.
yeah, of course, yeah. That's certainly best. Yeah.
What is the underlying?
Oh, this one. Okay, so this one is. I even forgot what I but θ3. Okay, θ3 is new and θ4 is. Yeah, good question, Leslie.
They shouldn't be.
Yeah, any other one was some internal thinking, and then I think I forgot. But it doesn't have any connection to mathematics. It's just like when you think something. Okay, that's just. It's not important. You just get forget. Okay, forget about underline. Underline is not here. Like it's just something else.
How do you read this off the geometry? Is this equation to then like geometry?
Yes. So, as I said, this picture describes you the image of your embedding. So that describes you the image. So that's quite allows you. So when you realize something is a projective variety, it means you have equation on the coordinates, right? Which guarantees you. So you take a simple multivector, right? And you have it. And so if you write, and so if it satisfies this, and ask it.
Actually, can you read us the polynomial?
It's a Plucker from underline means the variables that are being mutated. The variables that are being mutated. That's what the paper said. But yes. I think it must be Ted wrong, but I don't like his mutations, honestly. This I disagree. Oh, okay, they mutated, they don't mutate it here. So that's for sure. So what he wants to say, okay, I don't like his. So, but anyway, it doesn't mean any mathematical. It means he wants to stress that this equation, I guess he wants to stress, he wants to think about this governing, so like them together, different, like going both ways. I like to think this goes one way, and this equation governing mutation going from, so we have a new expression for new variable θ3, right? In terms of, so in place of θ3, we took this, and this just got, so no, anyway, so it's all. It's just a matter of how you think about it. Okay. So let me show you. So, okay, so that's odd mutation, right? So we have two types of different mutations. So that's, I think, is different from Greg, because I think you have one type of mutation. Tell me if you're wrong, if I'm wrong. I think one type, because I'm still in the waters of Techmura trying to figure out everything. Okay, so then we have also another type of mutation, which is called even mutation. And in even mutation, I can explain you what.
Now, what of those are the ones for the
Oh, forget about that.
Things that they do.
No, I don't like that.
Okay, can I
Yes.
So Greg says yes and no. We have even variables mutate and odd variables mutate.
Simultaneously or indifferent in
Greg, you can unmute. So yeah, he says simultaneously.
yes. So okay. So this is the difference. So in his case, he has one. Greg, you can interact. So what I understand, he has one type of mutation. So from like one type of mutation, and during this mutation, both even and odd can mutate. So they have like, but it's one type of mutation. So, but we have two different types. I don't say it's better. I just say it's different. Well, so different types of mutation. And in a previous type, odd mutation, we have only odd variables mutate, only odd. In the second type of mutation, which is like used together, we have both even and odd. For what it was, we have. So good or bad, I don't know. But mnemonically, you can remember it, you can memorize it this way. So if you want, okay, so usual without dots, right? Your usual mutation happens what? 3, 5 swapped in 1, 4, right? And mnemonically very easy to remember that, okay, dots, if you have this decorated, they kind of flip and drag endpoints with themselves. That's all you need to know. You don't need to know. And just this rule, and then this equation, the first being just a classical Plucker written down, forget other ones. So the second one is, and the second is this one and this one, they just, and if you look, that's very interesting. How, if you look at them, well, this one first, of course, you know perfectly well. Look at this one. So what happened? So the division, right, the denominator is 1, 4, right, is exactly where we come from. So that's this exactly diagonal which we mutate, right? So we mutate 1, 4, theta 1, and theta 4. So we mutate this dumbbell. We mutated dumbbell into another dumbbell. The whole dumbbell mutate. And this dumbbell, right? So, and we have a new dumbbell made of T3 theta 3 and theta 5. You see, one dumbbell, and it's properly from point of view, I guess, from class algebra, because you're a specialist here, that look, you express them also, you divide by 1T4, so which is as it should be, right? As you kind of expect that it should be, right? And your thetas, my new thetas, theta 3 and theta 5, right? They expressed in terms of theta 1 and theta 4. You see theta 1 and theta old thetas, they are expressed. And besides this, let's look at the coefficients, right? So 5, 4, 3, 4, they're nearby indices, so they are frozen, right? It tells you they're frozen. And okay, what is 1, 3? 1, 3 is another cluster variable, so it's legal, right? It's part of my cluster. And 1, okay, so, oh, and 1, 5 is also frozen, it's nearby, right? So it's also nearby, so it's frozen. Okay, so by the way here, yes, so Greg, where we have minuses appeared, which you may be wondering. So you see here, for example, you have 5, 4, and what I said before, so if you have 5, 4, it's negative 4, 5. So that's why when you're sitting and wondering where we have minuses, we do have. But similarly, we also have minuses in your classical Plucker, the first one. So whenever you write your classical Plucker relations and you have here, let's say 2, 1, I will flip it and have negative 1, 2. So that's we also. So that's where so yes, we have minuses, but yeah, so this one.
So do you have the expressions which are linear theta?
Yeah, they're linear expressions in fact.
Linear is fine, but now what happens is you have two thetas in one.
You want to have a product?
The theta times theta, and you need to have at least 6 of them.
Well, in these relations, you're not going to, so whenever you have, in the case of 2, 0 in Mn, you're never going to have products of terms. Never. They're going to be always like linear. But you are right, if you go up, if you go down, we're going to have a product interaction. And then we don't know, we already have a hard time constructing this, so we don't know how to, what to do basically. So this construction, I think I can, so okay, so let's just to show you now functor. Okay, so how much, now you can understand this. So in case of when you have just 2, 4, like 2 planes and 4, you have just simple exchange like this. Dumbbell exchange with this dumbbell. Now you know notation, easy, so this formula, and the cluster you know yourself, it's T13, T1, Now, what happens in 2051, which one I was explaining? So you have 2, right? So you have, in fact, 10 clusters always have 2 even to 1, right? And the big picture is this. So for you, from your perspective, how it looks like, it's pretty much your picture. You know how you have a usual exchange graph of pentagon? So it's like squeezed between additional. So you say like odds are squeezed in between. And I think, so it looks like I could compute everything. So this is a crazy picture of myself. So which I tried to do for 6.1. So I still don't have a good picture for this because it gets complicated. It gets more interesting and complicated if I try to apply this for 6.1. So it seems that this all logic works. So it seems to be, I don't yet, so I think I can prove, well, I computed quite a lot of general like sequences, like a first sequence, but in generic case, so that I could think that I can almost prove soon the Laurent phenomenon, which Misha said to me very important in the second mission. So I think I can prove it. So at least I proved like, you know, like a basis of induction and the stuff. So I think that's kind of, but I don't, it's just, I didn't prove it yet completely, but I think it works. I have like already enough. But, but yeah, so this is what we pretty much have. So we have, again, we have for this one, for our candidate for cluster algebras, which may be corrected, maybe even. So which seems to be similar to what Minnesota team has, Greg, Ovenhouse, and John, but they, you know, it's so different. Similar and different, but this is different for sure. I looked, it's different.
I think I don't know if Greg can record or was can confirm, but in even mutations they have like tops.
Yes, they have. I know they have in even they have usual Plucker, and then they have listen. They have a bracket, and then you have 1 plus, and then another term which also have container. So you have like addition. In my case, I have just Plucker, just usual one of the relations. What can I say? It comes from real computation.
So your human life doesn't include any odd variables, so it's kind of completely separate.
Yes.
What happens in human variable is just usual cluster.
Right, but it's also, Misha, it's also the same as how you interpret this relations. So, well, no, the thing is what I mean. My suggestion for cluster algebras, yes, you're right. So when you mutate even variables, even clusters, you have even cluster variables. You don't, in the formula, you don't have sets, right? That's true. Right. Unless you, I don't know, some kind of, because what I mean is, what I try to say is the following. So you have these relations, right? And you can have for others, for 2, 0, and 5, 1, and others, you have other relations. And the fact that we constructed cluster structures and we, in exactly this way, and selected clusters this way, is our choice. So, and who knows, maybe somebody else look at this and say, oh no, they shouldn't be doing this, they should be doing whatever that, because obviously that's not. And then one last thing, which I wanted just to show you, is that, and also these relations have very, very nice properties. So I have 3000 lemmas which is like, if you do this and this, you get this, oh, and this, so very, very nice kind of lemmas about these relations. So if you do this relations, you go back to this. If you go this and this, so it's like very, very nice. So it seems to be very, very nice, lots of nice properties about them. But yeah, so I don't have the final answer. And then here's the relations for, because I said we have relations for all. We have relations for RS in NM, but they are big. But here, example, 1 place in NM spaces. So remember, you have star, and star comes with variables from another one, from when you have Grassmannian star. And then if you just yeah, so this is alternative way. So this one uses, you need to know what Grassmannian is, but if you don't want to know, that's just at this one. And here, right, we have already a different kind of relations, and you would see that, yes, so it's already, yeah, it's already nonlinear, and so you have, but we didn't do anything with them, so just. But still work in progress. Thank you.
Let's thank Ekaterina. Okay, are there any questions?
Yes,
Misha.
So this is silly question, but so is it easy to see immediately that each of the clusters determines point in your Grassmannian? So if I know T1 3, T1 4,
No, it's not
T1 4, that should tell me exactly what the quantity Grassmannian is.
too easy to say. So if I have, I think it has to be,
No, after fixing frozen.
yeah,
Yeah, frozen is a fixed.
yes, I think we could easily.
So it's the same. It's the same.
It's a question about algebra, right? So
Yeah.
Yeah, that's
we
it.
have enough equation to
Yeah,
find
that's-
all
that's-
other.
Yes, because we proved in all cases it's embedding,
Ah,
meaning one-to-one. So you could,
But embedding, so for embedding you use all of this information. But if I just know this and frozen.
So the question is basically, if you know theta 1 and theta 4, then you construct the rest of the operators.
Oh, I said, yeah, I think yeah, so yeah. Because we're flipping and then moving, yeah, sorry. Yeah, it follows from your picture. Yeah, thank you. Yes.
so,
I'm no longer confused.
CK file.
Now you explained it well.
so I think it's a nice mnemonic rule.
No, it follows from.
Yeah,
the-
because from mutation there was a, yeah, so.
So, but of course, we are very new, nice and never had any experience with clusters. So all from Misha's and Misha's problem. Thank you a lot to the Misha who gave us this problem some time ago. But we of course, yeah, so looks like nice mnemonic to build.
And, well, do you know if you have any two forms? Invariant conjugation or
I
like
think
40 Tichner.
so. I was thinking about this. I think we can construct. So we actually discuss it. I think I'll have to think about it. So Misha told me also. I talked to Misha. He said you should have like. I asked, how do you know it's real, like a real thing? And so you have to be happy. so yeah. I'll give me a little bit of time. I know what you mean. So whether we don't have it right now.
You didn't check.
No, but I think I know where to get.
Okay, Greg has a question.
Yes.
Would you like to say it, Greg?
A few questions, but I guess I'll start with this one. Very nice talk, Ekaterina. So my first question, I just was trying to better understand. When you have GR20 inside Rn plus 1, it looked like when you were looking at 5, 1, and 4, 1, you ended up having two even variables and two odd variables in a cluster. But I was trying to understand like how many that would be for general N.
So you mean that at the moment we have m equals to 1, right? And you're asking how many?
Oh no, I think, sorry, I thought that was, yeah, this example would be N equals 5. And in each cluster you have two even and two odd.
Yes, and in 6-1, you're also going to have the same. So that's so let me see. In 6-1, so sorry for crazy picture, but I didn't want to type it in the and it's also I don't know the shape yet, but to make it work. But for the 6-1, we also going to have two odd in each cluster. We're going to have two odd, for example, here, two odd cluster variables and well, 3, 1, 2, 3 even.
So then would it be expected that if this was 7-1, 8-1, etc., the number of even variables in the cluster would grow as it usually does, but the number of odd variables in a given cluster would still be 2?
Yes, yes, that will be in this case. In this case,
Into 0.
yes.
0, okay.
If you, yeah, if in this, sorry, in this.
Yeah.
In this case, yes. But in other cases, the relations are such that I don't even know yet how to divide them into clusters, how to understand what, because you look at the relations and try to figure out what cluster should be. I don't know, but here in 2-0, so clusters algebra, we only talk about this. Because this one we figure out how to construct, I think. But again, not, I don't claim its definition, I claim it's a good standard. But yes, you're right. There's going to be always in all these cases, right? So you have, so I don't know what
Yeah, she's pointing at 2-0, the case 2-0 and 1.
So we consider, so we proposed cluster algebras or hypothesized for 2-0 and 1. And for 2-0 and 1, in our construction, which I can draw for you infinitely, it's have always have two odd in every cluster, two odd cluster variables and 3 even clusters.
Okay.
So even you all know how many even going to be, because even, as you could see from these triangulations, comes from just usual stuff which you know very well. But odd is always going to be the end of one of the property. So Lambda is going to be one of the numbers. So
Okay.
So, yeah.
Misha.
We have this initial conversation, and yes, if you have like any m, like G20 M,
yeah,
it seems like you can consider this just all what variables are decoupled. So you can for each what variables you can just put two what variables on each value.
how many
Add couple of
for each? Yeah.
what variables on the side, and just repeat the procedure and everything just goes like, because all
You
the
think I will be
formulas
able to do
decouple.
it?
It seems like all the formulas decouple. You just
I'll
don't-
try. I'll try to do it.
And
And
probably for K0, you'll just need K for the variables in each cluster.
and
so you
For
think,
K0,
Yeah.
for
for K0, K, yeah, so you just have to mark one of these Plucker's mark it with red dots.
yeah, just use colors for your dots. Yeah, you have like one red, one blue, one
pumping. Okay.
one.
Okay. That's a good suggestion. So I'll try. So thank you very much, by the way, for all this productive. So I was working all the time, thinking. Yes, you have a question? No.
Okay. Okay, I think let's thank Ekaterina again for this nice discussion.